Here's this concept of hybrid consensus. This is going to lead us into Grandpa. This is the abstract from the Grandpa paper right here. And I'm actually just going to read it, even though it's a whole paragraph long, because I think it's super valuable. All right, so classical Byzantine fault-tolerant consensus protocols, like Tendermint is based on, forfeit liveness in the face of asynchrony in order to preserve safety. So that's what we saw with Tendermint. When there's too much asynchrony, when we're not getting Tendermint votes through fast enough, we throw the whole block away, and that's what they mean by like forfeit liveness. Whereas most deployed blockchain protocols, so at the time when this was written, that's talking about proof of work protocols like Bitcoin, for example, forfeit safety in order to remain live. What that means is that we have this idea that you can always reorg, nothing's ever truly finalized, but the advantage is that the chain always keeps growing. So they're contrasting classical BFT versus blockchain. Classical BFT says, if we're not finalizing, we're not doing anything. And blockchains like Bitcoin say, we're always staying live whether we're finalizing or not. In fact, we're never going to deterministically finalize. Let's see, in this work, we achieved the best of both worlds by proposing a novel abstraction called the Finality gadget. A Finality gadget allows for transactions to always optimistically commit, so the chain remains live, basically, you keep the authoring going, but informs the clients that these transactions might be unsafe. So we see new blocks coming in, we add them to our database, but we know that there's always a chance we're going to reorg away from them. As a result, a blockchain can execute transactions optimistically and only commit them after they've been sufficiently and provably audited. In this work, we formally modeled the Finality gadget abstraction. Okay, blah, blah, blah. That was the part I wanted to read. Thank you for bearing with me there. So this is the paper that goes on to introduce Grandpa, which we're going to talk about next. But I think one of the biggest contributions here is not actually Grandpa itself, but this notion of the Finality gadget and the notion of allowing the chain to stay live and keep authoring blocks, even when Finality is stalled, with the hope that Finality will come back shortly and catch up. So, Grandpa provides deterministic finality only. Tendermint provides deterministic finality and block authoring. So when you're using Grandpa, that means you need some external authoring scheme. So it could be Aura, it could be Babe, it could be Sassafras, it could even be proof of work. You could even go back and use old school Nakamoto proof of work authoring and then use Grandpa as a finality gadget to finalize your blocks deterministically, so you'll never reorg away from them. Kind of like Tendermint, but better, in my opinion. And the key difference here is that Grandpa finalizes whole chains of blocks, not just individual blocks. We don't have to run this finality protocol at every single block. Now, when things are going well on the network, that's exactly what we do, because it's nice for finality to stay close to the tip. It makes it unlikely that we'll have deep reorgs. But when things start to go bad and finality starts to lag, it gives us the ability to say like, oh crap, something bad happened, finality is now 20 blocks deep, we don't have to run 20 rounds of Grandpa to catch up. We can actually just run one round of Grandpa and finalize all 20 blocks in one swoop. So here's like the main thing that I think is so much cooler about Grandpa. These finality protocols, these BFT-based protocols, Byzantine fault-tolerant protocols, they have high messaging overhead. They're all O of n squared. So that means that their graph is like parabolic. It goes up, which is to say, as you add more authorities, as you decentralize the network more, the time complexity of the finality really increases. It's super linear. It's worse than linear. But the block authoring schemes, those are only O of n. You just author a block, you gossip it out to your n peers, and that's it, you're done. So it's linear. So the time complexity of these finality games is inherently worse than the authoring games. And when you tightly couple those or interlink them like you do in Tendermint, that means you have to slow down the authoring to match the finality gadget. What we do here when we separate them, when we do this hybrid consensus thing that I was just reading, is we allow them to operate separately. We allow the authoring to happen in O of n, which is as good as it can get, and it doesn't have to be constrained or throttled back to the O of n squared that the finality gadget requires.